Hi, this is Professor Fernandez. In this video, we're working on example 3.10 from Calculus to Simplified. This example is about finding the the volume of a solid with a known cross-section. In this case, the cross-sections are perpendicular to the x-axis, and they're taken to be equilateral triangles. So if I zoom in here for a little bit, right, there's a region. So the region is bounded by the graph of this function, this other one, and x equals 0. So you can see that one of these is the line that's sloping down here. This is f of x. This is y minus 2x. The other one is sloping up here. This is g of x. So this is g of x. This is f of x. And g of x is negative 2 plus x. And so the region between those two curves and bounded by, up here, bounded by x equals 0. X equals 0 is the y-axis. So we're talking about this entire region. So that's our region. Now from that region, we are going to construct equilateral triangles. So that's what's going on over here, right? If I try to extend the y-axis here, this would be behind or underneath really this kind of pyramid, and then the x-axis is over here, and these equilateral triangles are coming up. So you can see here's one of them, and then here's another one coming up. Okay, so it's like if I drew my little base here and I have equilateral triangles coming up. Here's one, and here's another little one. And I fill this out to generate this sort of pyramid-like solid. So the question is, what is the volume of that solid? Well, we learn in this section in the book that, and I'll flash the theorem down here, that if I know the cross-section of a solid that's been generated by adding up, if you will, these cross-sections, and if the cross-sections are perpendicular to the x-axis, then the volume is given by this equation. Right, so I need to first figure out that region on the plane. What is the smallest x value? What's the biggest x value? And I need to figure out the area of a cross-sectional slice. So I'm going to go back here, and I am going to, weave all that together. So I have my bounded by x equals 0. That is going to be my a value for my integral. And then the region stops here. So this is x equals 2, so that's going to be my b value. So I'm going to set up here my volume. I already know my a value from 0 to 2, and I need to find a of x. Remember, a of x is the area of that cross-sectional slice. I have to zoom out here. I'm told that the cross-sections perpendicular to the x-axis are equilateral triangles. So it turns out that equilateral triangle cross-section areas, you have a very simple formula for them. And it's root 3 over 4 times s of x squared. This is in figure 3.7 in Calculus to Simplified. So I made a figure to give you all these, usual square, semicircle, equilateral triangles, cross sections that are usually asked for in calculus books and tests. Okay, so what is s of x here? S of x is, if you look at the region that you're drawing in 2D, right? S of x is whatever sort of height this cross-sectional area has. So for example, here's a triangle. So in the xy plane, you're looking for specifically this height, right? So I'm drawing here things in 3D to show you how that height becomes the base of this triangle. If I now go to 2D and I look at this region here, and I'm looking at this same infinitesimal rectangle, then that's why I keep calling it height, because this is a change or a difference between whatever this top function is and this bottom function. So if we go back over here to our picture from figure 3.9, this is the infinitesimal rectangle that I've drawn here. So if I'm looking for s of x, right, it is the sort of height of this little rectangle. And to find that, well, I have to take this y value, right, and subtract this y value down here. So the height is 2 minus x minus negative 2 plus x. That's my height. That's my s of x. So 2 minus x minus negative 2 plus x. What does that give me? Let's simplify. 2 minus x minus negative 2 plus 2. And then minus x, right, minus x. So that's 4 minus 2x. Okay, so I've gotten my height of my rectangle. And at this point, it's always good to check that things are making sense. So if I'm looking at this height of my rectangle, I would like to verify that I've done all my math correctly. Because one thing you might wonder is, well, should I have subtracted? Maybe I should have added, right? Here's a way you can check your work. So if I look at my graph and I put my rectangle a little bit to the left, let's make it all the way over here where x is 0. We can just see that this would be 2 and this would be 2, that would be 4. So 4 at x equals 0. That is, in fact, what I get from my formula. And then also over here, as I push my rectangle all the way over here, it becomes basically a point. So the height is 0. So at x equals 2, if I put x equals 2 here, I get 4 minus 2 times 2. 4 minus 4, that's 0. Also makes sense. So this is giving us a good indication that, in fact, right, it passes a couple of checks. This is our s of x. This is our height of this infinitesimal rectangle. All right, so now I'm going to use that height of the infinitesimal rectangle, s of x, as the base of one of these equilateral triangles. And like we said before, the area of that equilateral triangle is given by this formula. So now I'm going to switch back to red here and say, okay, I now know what my a of x formula is. It is root 3 over 4 times 4 minus 2x, right? That was my s of x, all of that squared, dx. So now I have my integral, and honestly, the rest of the problem just reduces to integrating this. We'll go through it, but we've done the most difficult part, figuring out the a of x, working with the region and all that stuff. Okay, so I'm going to pull out the root 3 over 4, integrate from 0 to 2, and I am just squaring this out. A couple of things you could do for this integral. If you don't want to square it out, you could use integration by substitution. You could, for example, let u equals 4 minus 2x. du would be negative 2 dx, and then go off and do the substitution. Or you could do what I'm going to do here, the more straightforward approach, and just square this out. Right? So if we square this out, we get 16 minus 2x times 4 is 8x, and double that. So that's 16x, and then 2x squared is 4x squared, and then plus, because we're multiplying negative by negative. Okay, so we get that integral. And then from here, we would just apply the integral version of the power rule. Antiderivative of 16 is 16x. Antiderivative of that one is add 1 divided by the result. Antiderivative of that one is same thing, add 1 divided by the result. And then integrate from 0 to 2. So evaluation theorem eventually gets you to a number, and here is that number. I always like to double check that the answer that I get for an integral makes sense. So first of all, we are supposedly calculating the volume of this solid. So volumes are positive, right? Or 0. You can't have a negative volume. I can't, fill a bowl of water and get negative, 10 cubic feet or something. So for sure, we've gotten a positive value, so that's good. So that gives us a good indication that we're on the right track. Other things to check, right? Make sure you use the correct formula. This is, like I said, the formula for cross sections that are equilateral triangles, right? Perpendicular to the x-axis. If we had been told they were semicircles or squares, slightly different formula. So then your integral would be slightly different. Next thing to check is that you've got the right bounds. So we're only going from 0 to 2. We talked about that because this is the region that is the base of this solid, right, that we are finding the volume of. All right, so once you've checked all that stuff, you're reasonably confident, right, that everything is working out as it should. Then I think you can step back and say, okay, I'm pretty sure that this is in fact the answer. All right, see you next time.